Okay, so we just put stuff in the bags. We put the carbon dioxide in a bag, and we're measuring basically our temperature with air. We're looking at what our air is actually made of. And so that's what this whole module is about. We are addressing our atmosphere. So once again, we look at big pictures, and then we just start breaking down individual sections. In our last module, we looked at the actual makeup of the earth, the hard portion, and now we're looking at the spot on the outside. And the thing that I hope that you walk away from this is we have covered a lot in this class. From the beginning of August all the way now, we only have 3 weeks left after this. And we've gone from very small molecules to actually how you make up everything, how does it work. Then in our last module, we were looking at the earth itself and its structure, and now we're expanding out. We're looking at the atmosphere. We're going to be studying space with that. And what we continually find is that there is divine order with that. And so I hope as we've gone through all of this, it just leaves you in awe of like, God's order is so amazing. He has such a plan. There is such a design. And even things that we just take for granted, especially like air, we don't even see air. We see the effects of air, right? But we don't know exactly, like we're not walking around going, oh, there's oxygen in the air, there's nitrogen in the air. But it's important. All those pieces are valid. So when we're talking about the atmosphere, when we're going from just the earth, when we're, from the rock part of the last module, as we expand out, when we address the atmosphere, we are looking at all of the air surrounding a planet. And there's going to be different layers. If you didn't read about it this week, you will this next week. There's going to be different layers within this, just as within the earth, we had some different layers and they had different functions for it. But as we look at this whole air around the planet, we have a couple of things that we notice. First off, you would think that oxygen is the number one gas in the air, right? Because we all need oxygen to breathe. It is not. Nitrogen is our number one. Nitrogen, and the fact that nitrogen is 78% is one of the reasons that we're alive. One of my other sons did an entire report on cellular respiration, and the number one thing that makes cellular respiration possible is nitrogen. And so if we didn't have nitrogen, we wouldn't have plants. If you don't have plants, you don't have the ability to change carbon dioxide back into oxygen. If you don't have that, we don't have the ability to sustain life. So nitrogen is the number one gas that allows for life on a planet to exist. So then we have oxygen makes up the other biggest portion, and then we've got a whole lot of gases that are the last little percentage of it in the air, okay? But what are the ones that are most important for us to be alive? Well, nitrogen's not super important for us to be alive. It is for everything else, or plants to be alive. But for us, we live in a cycle of oxygen and carbon dioxide. So I had a little plant, I had a little guy here, and we breathe in oxygen, our bodies use it. We expel carbon dioxide, as we did into the bags for another option for our experiment here. And then organic matter, plants, trees, all of that, they breathe in our carbon dioxide, and through photosynthesis, they expel oxygen. And so we have this beautiful cycle where, they often say put a house plant in your house and it'll help clean your air in your house, because you're in your house breathing out your carbon dioxide. Your plant will take it out of the air and give you some more oxygen in it. So this is our cycle that we need, our carbon dioxide to oxygen cycle, okay? So just as we had our water cycle, keeps our water rotating in all the different areas, we have our air cycle for that. And then what does our atmosphere do? Well, we learned last week that we have some magnetism, right, in our earth, and that it repels a lot of what's coming to us from the sun. So we have our solar rays that are coming down, and not only is the earth repelling some of those solar rays, but we have this layer of air around us, our atmosphere. And as the rays pass through, some of them get repelled by the atmosphere. Some of them make it all the way to Earth and actually get absorbed. Like if you have a black shirt on a hot day, it's gonna absorb that. And that ties in our light study, right? Because light is really energy. And so when it is trapping all of the light, then you've got more energy within you. So, you know, a black shirt is going to have more energy within it than a white shirt is, so it's gonna be hotter. All the same cycles, they all tie together. But then, because of the Earth's magnetism, some of those rays get reflected back out as well. So we're taking in some, we're pushing some away. When you're in space, or if you're in a good thing is even on Earth, has anyone been to the desert? Like Albuquerque, Arizona, anything like that? There are hot deserts. There's actually tundra deserts, like anything above like 6,000 feet is also considered, can be a dry, cold desert for it. What happens when you go to a desert? You might need a sweater in the morning, right? If the sun's not out. But then you're in a swimsuit by 2 o'clock, and then you might be in a sweater again in the evening. When I lived in Phoenix, I always had a sweater in my car, even if it might be 100 in the afternoon, because the sand is reflecting all the heat. It's not absorbing anything, so we have these large temperature changes. So with our Earth, they pose the question in your book, what keeps our Earth from not being like, when we're the part that's turned away from the sun, and the sun's, you know, it's nighttime for us, what keeps us from not plummeting in temperatures? Because we don't have any rays going there. That comes from the absorption. So our Earth gets to absorb some of the heat, but as it's reflected out, we have this layer called the ozone layer. Okay, so it's a special layer that has more of these gases in there, and that's what we're looking at as our experiment is going on, is that we've got carbon dioxide, we've got the nitrogens, we have these extra gases, and they absorb these rays, they absorb the energy. And so it's kind of like putting a little blanket around the Earth. So the Earth has its own heat that it's taking in from the sun, but then we have this regulation of temperature where our atmosphere has absorbed some temperature, these gases, and there's only so much that they can absorb. So then it makes sense that God had to put the right amount of gases in there so they don't absorb too much. When they get full, then they're full and they let the rest of it go through. And so they maintain a temperature for our Earth all the way around, okay? So the greenhouse effect that we're looking at is how do these gases actually trap heat? What part of, so they're taking in the energy that is coming in from the solar rays, and when we hold energy, energy is converted to heat, right? It's a byproduct of that. And so it's actually trapping it and kind of putting it around the Earth like that. So the difference that the book wants to address between global warming and greenhouse effect is often they're used at the same time, but in reality, the greenhouse effect is necessary. I have a greenhouse for a whole bunch of little seedlings right now that will go in my garden. It's a plastic cover, you know, it keeps the heat in, it keeps the temperature regulated. We need our little plastic cover around Earth. We need to have our temperature regulated. We need there to be consistency there. We need to have the greenhouse effect. Global warming is when we have too much heat that stays in. And so there's lots of TED Talks on that. There's lots of different theories that we can go into. But God has a design and an order, and I think we are required to take care of our planet for it. I also believe that there's a lot of ebb and flow of things that we don't know, and how God orders it. And so usually they'll throw a big fit about global warming, and then tides will shift or change, and we'll see some backup on that as well, okay? So carbon dioxide, what are the things that we know about carbon dioxide? It has an oxygen in here. When we were studying atoms, what type of reaction always had oxygen? Combustion. Excellent. Combustion always had oxygen with it, okay? So carbon dioxide is a product of combustion. Combustion produces heat, okay? Heat can be in the form of energy. So what our bodies are actually doing are combusting. If you think about it, we're breathing in oxygen. It's combining it with the food that we have made, and it is causing a reaction, a combustion reaction that produces energy. So that gives us the energy to move, right? Energy is neither created nor destroyed. It's got to come from somewhere. So we take in food, we take in air, it reacts, and we get to use the parts that we can use, and the byproduct of carbon dioxide gets expelled and not used as we breathe out for it, okay? So when we are dealing with all of this, our second lab today, we're gonna be looking at pressure. So we have this blanket of air. Our atmosphere actually it keeps our air inside, right? So it contains it, so we're not just like going out to space. We know that space is a vacuum, so it doesn't have the air like our Earth has. We don't have this. And so how does this air work as we're in here? So in some ways we can think of the Earth does have a magnetic pull, so it's pulling things closer, right? And our gravity is keeping us on Earth and not floating out into space. And that gravity pulls on everything. And air actually has a weight. We don't think about that a lot, but it's made of molecules. The molecules have a weight. We learned that at the beginning. They have a mass, right? And so as they get closer to the weight, it's going to be pulled. And so everything that was spread out is now getting condensed a lot more. Has anyone ever been to the Science Museum where they have the bed of nails? Okay, and laid on that bed of nails, whatever, okay. When you lay on the bed of nails, is it super painful? No, because your weight is spread out over each individual part of the nail. Now, if I asked you to stand on the bed of nails and stand with 1 foot, do you think it would be painful? What if I asked you then to get up on your tippy toes? Would it be painful? Yes, it would be painful. So all of that has to do with pressure. When we talk about pressure, pressure is, you will need this for the test, force over an area, okay? So the amount of pressure that somebody is pushing is the amount of force over a certain area. So if I am applying pressure to this entire chair and I have my hands spread out, my area is larger and my pressure is going to be smaller than if I apply all of my pressure to 1 point on the chair, okay? It's the same difference as somebody, poking or pushing on your arm with a hand or pushing with a finger. It's gonna feel a lot different, right? So when we look at pressure, we've got force over an area. So let's look at what it does mathematically. If my force increases, one of the things that I've been teaching you guys is that when we're on opposite sides of the equal sign, they're both in the numerator on opposite sides of the equal sign, this is a direct proportion, right? If one goes up, the other one goes down. Direct proportion. Yeah. The other one has to go up. So is that true? If I keep my area maybe 1 square centimeter, and my force is 3, then my pressure is 3. My force goes up to 4, I'm up to 4. My force goes up to 5, I'm up to 5. So we can see that mathematically when we look at pressure and force, when the area does not change, is a direct relationship. But what happens when I have pressure and area? My force doesn't change, okay? That is going to look like an indirect relationship, which means as my area changes, my pressure goes down. So in this, my area kept getting bigger and my pressure is now decreasing. So we've got direct relationships between pressure and force, and we have indirect relationships between pressure and area. Do you want to stop and go check them?
Yes.
We'll come back and we'll talk about the rest of pressure and then we'll do that lab. Okay, so when we did the reaction between vinegar and baking soda, we 100% know that the only thing that is produced is carbon dioxide, right? So our concentration there with that carbon dioxide versus when you're breathing out, there's carbon dioxide, but there might be other things that you're also breathing out as well. It's not that, it's not as concentrated on that. Perfect. Oh, where did I put my little clicker? Me and my clicker. Honestly, isn't it? Okay, so pressure, as we have our atmosphere, as it's pushing down, it's a gas, right? So we know some things about gas. We know that gas wants to spread out. The more space that it has, it's going to spread out more. So as we go out into space, our gas is going to spread. As we get closer in, it's going to be more dense. It's going to be packed together a little bit more. So I have all my little molecules. If we have air molecules, when they are down at sea level is our control. It is our baseline. Okay? Who knows the lowest sea level on Earth?
The Dead Sea.
The Dead Sea. Excellent. Okay? So you can be below sea level. I grew up South Louisiana, we lived at 6 feet below sea level. You can be on a mountain and you can be above sea level. Okay, but sea level is our baseline for it. We are going to measure pressure as the force over a certain amount of area, and when it is at our sea level, at our baseline, we use atmospheres. So the two things that we're going to need to know for this class, they gave you a whole long list of all the different ways that you can measure pressure, is atmosphere and PSA. So pounds per square inch is what that stands for. So an atmosphere, one is at sea level. If it gets higher, that means you're going higher above sea level. If it gets lower, you're going lower, below sea level. Okay, so we have this air, it's down close. The closer it gets, it's more packed together. When it's more packed together, we have more molecules in the same area. So we have more force. If all of these are applying, say, 1 of force, and I can fit 6 of them inside this area, then my pressure is going to be 6. That makes sense? But as they spread out, now in my same little box, they spread out, so now I only have 5 of them in the box. So now I have 5 over the same area, so my pressure has gone down, right? Because I have less applying a force. So the higher that we get in elevation, we have fewer and fewer molecules that are pressing down in a certain amount of area. So because this is a direct relationship between pressure and between force, less force in that area means we have less pressure. So when we raise in altitude, we have a decrease in pressure that's actually pushing down because we have a decrease in the amount of molecules that are in that area. Does that make sense? Any questions about that? Okay. Now, a barometer, who took track of their barometer this week? Anyone keep track like I asked last week? We've basically stayed, I have it on my thing. We've basically stayed sort of between 29.5 and we got up to 30.8 is where we went. It doesn't sound like a huge difference, but it can be a really big difference. I was specifically looking at the days that we had the fires and then if we had any weather storms to see if we could see some of the change for that. So be sure to check your barometer each day this week. Make note of that for it. So how does a barometer work? A barometer kind of looks like this. And if anyone has ever been in a pool and someone jumps in, the water splashes out, right? Because we all take up space, and if something moves into your space, you have to move. If I'm in the chair and my husband comes sits with me, he's either gonna be on me or I've gotta move, right? So we can't take up the same space at the same amount of time. And so as our air, these molecules, is pushing down on the liquid in the barometer, if it pushes down more, then the liquid has to move up. So an old school barometer measures the weight. If you push down more, then it's going to squeeze up through the center. Kind of like a toothpaste. You know, if you push on one side of the toothpaste, it's going to squirt out your toothpaste. The other side, it has to go somewhere. So in this case, it just moves up. So our barometer says that there has to be some equalizing. If there's pressure on one side, it either has to go somewhere or there has to be force pushing back. So as we look at pressure in our next lab that we are going to perform, we are kind of addressing Newton's laws back in that module when we said every action has an equal and opposite reaction, right? Every force has an equal opposite force that's pressing on it. Same with pressure. We don't collapse under the weight of the air because our bodies are pressing back against the air. Otherwise, we'd all be puddles on the floor, okay? So we're pressing in and out. When you have a water bottle and you drink the water out of it quickly and it crumples in, right? As soon as you let it go, it pops back out. Why would it pop back out? It pops back out because air is in there. If it doesn't, sometimes you do this and you blow in it to pop it back out. You are providing pressure on the inside to equalize the pressure that is going on the outside. Our lives love to be in equilibrium. Okay? We are designed to stay in equilibrium, our bodies are designed to stay with an equal temperature between 97.5 and 98, 99, degrees for that. So if we're too cold, we're going to absorb energy and motion to get heat from the outside. If we're too hot, we're going to sweat. We need our bodies to stay in equilibrium. And so with pressure, there's always pressure on the inside that is addressing the pressure on the outside. Spiritually, I like to think about that as we often have pressures on the outside that tell us what to do. But the more that you pack your inside with Jesus and with the Holy Spirit and truth, it allows you to have his pressure from the outside, from the inside, addressing the pressures on the outside for it. And when there's balance that's off, then that's when we can kind of feel crushed at sometimes like that. Okay, so even though we don't see it, there's always pressure. There's pressure being equalized on it. And when we address our cans, we're going to have two different parts of the experiment. One, where we are allowing outside forces to affect that pressure, and another where we are sealing off and we are no longer allowing any outside forces to affect the pressure. And we're going to see if we can visually comprehend the pressure that our air in this room is putting on us. That sound good? You ready to do that one? Let's go ahead and do it.